now that we have this idea of giving coordinates to arrays, let's start to actually look at the distance between points. So let's say I have this circle. So I have 4 points, O, C, M, and T, and then they have these coordinates 0, 8, 12, and 15, where this is essentially if I start at the point O and I move around counterclockwise, how many miles I need to go. So if I actually want to find the distance between O and T, then the old way to do it would say I would subtract these coordinates. 15 minus 0 is 15, but that's wrong since I won't actually be going around counterclockwise. I'll be going around clockwise, which is a much shorter distance. So instead, we have to think about it the other way. So the point M is directly above the point O. So the actual value for alpha here is 12.4. So we can say that 15 and 12.4 would be 2.6. So that tells us this distance right here is 2.6. So if to get from O to M is 12.4, to get from O to T should be that 12.4 minus the 2.6, which gives us a distance of 9.8. So essentially, we want to try to find a way to formalize exactly what we just did here. In order to formalize this, we need to start with a theorem. So here's our theorem, and we're specifically assuming that alpha is finite. Alpha is less than infinity. So let's suppose I have the betweenness relation PAQ, and I know that my line L is the union of the ray AP and the ray AQ, where the distance between P and Q is less than alpha. Then if I have any 2 points, interior points, B on the ray AP and C on the ray AQ, then one of these two things has to be true. If the distance between A and B plus A and C is less than or equal to alpha, then we know that BAC has to hold. And if the distance between A and B plus AC is greater than alpha, then we must have the relation BA star C, where A star is the polar opposite of A. Before we start proving this, let's note a couple of things. First, the ray AB is equal to the ray AQ, since both of them have the endpoint A and they both pass through points B or P. Similarly, the ray AC is equal to the ray AQ. This gives us that neither ABC nor ACB can hold. For instance, if ABC, then we know C is on the ray AB. That would mean the ray AB is equal to AC, so that would mean the ray AP is equal to AQ. And we can get something similar for the other case. If either one of these holds, then the ray AP and AQ are the same, and that would contradict my initial PAQ. So now that we've done that, let's start by proving this theorem, and let's start with part 1. So for the first one, by a previous corollary that I proved in the last video, either ABC, BAC, or ACB holds. However, we just stated that ABC can't hold and ACB can't hold, therefore we have to have that BAC holds. So that gives us part 1, and we can start looking at part 2. We know by a previous statement that AB, A star. Since A and A star are polar opposites, every point B is between A and A star. By axiom 5, we know that we have to have one of the 4 betweenness relations BAC, ABC, CBA star, or CAB, or CA star B, which is the one we want. If BAC is true, then alpha has to be greater than BC, but also that tells us that alpha is greater than BA plus AC. However, I already said that AB plus AC is greater than alpha, so that gives us a contradiction to our hypotheses. In addition, we've already stated that ABC can't hold. So I've now eliminated 2 of my cases. So now I have to consider the CBA star case. Now, if we have that CBA star combined with the fact that ABA star, it must follow that we have the property ACA star. So if it's true that CBA star combined with the fact that we know ABA star, it must follow that we have ACBA star. And that tells us that ACB must hold, which we previously stated is impossible. So there's another contradiction, and so we're guaranteed the one that we want, C A star B. Now that we've done the background, we can actually start to look at lines and how to find the distance between 2 points. So the points on a line can be placed in one-to-one correspondence with our real numbers x, where negative alpha is less than x is less than or equal to alpha, such that if I have 2 points, P and Q, with coordinates x and y, on our line L, then the distance between P and Q is the absolute value of x minus y, if that absolute value is less than or equal to alpha. And if it's not, if the absolute value of x minus y is bigger than alpha, then we can calculate the distance by 2 alpha minus the absolute value of x minus y. So let's look at some examples of using this. So I have 3 points. A has coordinate 20, B has coordinate negative 20, and C has coordinate 12. And I know that alpha is equal to 30. I want to find 3 distances. Distance between A and B, B and C, and A and C. So for AB, we start by finding the absolute value of negative 20 minus 20. That gives us 40, which is greater than alpha, so that's not going to work, and we need to use our other formula. The other formula said 2 times alpha, which is 30, minus the absolute value of B minus A. So that gives us 60 minus 40, so the distance between A and B is equal to 20. Now let's look at B and C. We start by taking the absolute value of their subtraction, so absolute value of 12 minus negative 20, which is 32, which is too big. So we need to use our other method. 2 times alpha, which is 30, minus this absolute value of 12 minus negative 20. That gives us 60 minus 32, or 28. So the distance between B and C is 28. Finally, we have A and C. We start with the absolute value of 12 minus 20, which is equal to 8, which is less than 30. So that one works. So now I have all 3 of my relations, and we can see that the distance between A and C plus the distance between A and B is equal to the distance between B and C. So that tells us that we actually have the relation BAC. Let's look at another one. So I'm going to consider the exact same points, but this time alpha is equal to 35. So let's start with AB. The absolute value of negative 20 minus 20 is 40, which is still bigger than 35. So we need to use our other method. We have 2 times alpha, which is 35, minus this absolute value. So that gives us 70 minus 40, which is 30. So in this case, the distance between A and B is equal to 30. Now let's look at B and C. When I do the absolute value of 12 minus negative 20, I get 32, which is less than 35, so there's my answer. For A and C, I have 12 minus 20, which is 8, so there's my answer. And if we look at these, we can see that if we add any 2 of them, we will not get the third like we did on the last one. So we have no betweenness relation between these 3 points.